We're going to come back around to this idea of fields. We've talked about this once before with gravity and gravitational fields. The idea with that and with this is that there's no actual direct force between these particles. So in this case we're talking about charged particles. Before we were talking about masses. So up until now we've been saying that each of these charges experiences a force, and that's just a direct action because the two forces exist. But if we were to, say, get rid of one of these forces, or one of these charges, then the forces would be gone, and we would have no effect of this charge in space there. Well, it turns out that not only is that a difficult model to work with for some of the problems we're going to do, it doesn't explain some of the behaviors that we see. So instead we think of this as more of an indirect situation, where the existence of some charge Q1, it causes some distortion in space, some field, we call this. And so now if I were to put a charge there, call it Q2, it feels some force as a result of this electric field. Now, this Q1 here may not be there anymore. It may have moved to a different location, or been annihilated in some collision with another charge, or something weird like that. But this field would exist for some amount of time anyway, in the absence of this charge. Turns out the amount of time is just how long it would take light to travel this distance, so probably not very much time. But this force would still be occurring even if that particle over here were gone, that charge over here were gone. So that's just one way that it's useful to think of this field as being what causes the forces instead of the charges causing them directly. So the field acts as an intermediary. Now, the electric field has some strength, and we'll call that E. E is the electric field strength. And we'll define the strength of the electric field in terms of how big of a force it could apply to a certain charge. So if we could say F here is equal to the force on a charge Q, then E is going to be equal to F, that force, divided by Q. So this is just a ratio of the strength of the force that a charge would experience to the amount of charge it has. And then the units on this are going to be, well, force is in newtons, and charge is in coulombs. So electric field is measured in newtons per coulomb. Now if we're looking at just a single point charge, like we have been talking about so far, so some charge, call it Q1 here, the electric field at any point in space, whether there's a charge there or not, can be calculated. That's the strength of this effect from this charge. So at any point in space, what we're going to need to calculate this would be, well, the electric field is the force divided by the charge Q. So the charge Q is going to be left as a variable here because we don't know what charge we're talking about putting at any of these locations. We're just looking at the general ratio. So we need the equation for the force from a point charge, which we've worked with before. So the electric field is going to be equal to 1 over 4 pi epsilon naught times Q1, Q2 over R squared, and then this whole thing is over Q. And we just kind of pick which Q we're talking about here. So let's say well, I guess I have this one labeled Q1 already. That one's going to stay where it is. So we're talking about adding some additional charge, Q2. So those two are going to cancel, and we get the electric field caused by a point charge is equal to 1 over 4 pi epsilon naught times Q. This is Q1. Usually we just write that as a Q, though. Q over R squared. And that as well will have units of newtons per coulomb. So if then we said, okay, let's take some charge with 5 microcoulombs of charge and place it at some location here. If we've calculated the electric field, we can just multiply the electric field strength by the amount of charge, and we get the force acting on that charge. Now, electric fields we think of as we assume that this charge here is going to be positive. So when electric field is positive, that means that we have the field going away from the charge. And when it's negative, that's going to be toward the charge. Okay, so if we have a positive Q1 here, then anywhere along here we're going to get a positive value then. So Q1 is going to be positive, R squared has to be positive, this constant is positive, so anywhere around Q1 we have to have a positive value for E, which goes with away from the charge. So if we were to draw this out, electric field would be pointing away from the charge if this is a positive charge. If it were a negative, electric field at any point here would be pointing toward the opposite.